includes an overflowing wine glass, so it doesn't know how to depict it. It's either empty or half full, and that's a fun fact I learned.
Okay, so we imagine that we are a computer. We also don't have to imagine we are a computer. What I'm going to teach you today is the perceptron. The perceptron predates computers. It was implemented mechanically before it was implemented in code. The perceptron was implemented or was first attempted to be solved as, I think, a master's student at MIT's summer research project in the 60s. Turned out to be a little harder than that. I do regard computer vision now as basically solved. Sometime between 2015 and 2018, computer vision technologies got better at recognizing images than I was, and the science kept progressing because not everyone has these. But like by the time the computer was better at telling it what type of tree something was than I was, I didn't really care, right? It's like, oh, the problem is solved, right? Computer vision frameworks are a little bit challenging to think about because of the quantity of information that is in the frame of an image. So I'm going to draw a frame of an image on the board. Okay, so we can think of this as an image, right? And we can think of it the same way as if we look out a window pane, and you can also think of it the same way as if you look out through your pupil, right? It is already taking a restricted subset of the world. Now, in order to make this manageable to think about at all, we're going to imagine a very simple world. We're going to imagine a simple world in which versus the millions of rods and cones that are light sensors in my eye that receive either lightness and darkness in the case of rods or color in the case of cones, I am only going to have a 3x3 grid of light sensors in my eyes, and I'm only going to be able to tell brightness from darkness. How is this going to work? I'm going to imagine, oh no, this marker is cursed. Does anyone see another black marker?
There are some dark ones back here, but they're not black exactly.
It's much more helpful to do this with black and white, so.
There's this one that's kind of still alive. It has no count.
Okay, throw it at me, I won't catch it. Oh my gosh. I did a 1 hour uphill treadmill workout on yesterday. I can't stand up, it's awful. Okay, so thank you. I was at 92% max heart rate for 1 hour. Okay, never do that. Okay, so we're imagining that we have only a 3x3 grid of brightness detectors in our eye. And we're going to imagine the example. We're looking at a very interesting world, but this world only has a few things in it. Specifically, we're only going to look at dice. So we might, for example, have something that looks like this. And what is this? This is a 6-sided die. And what would this look like if we looked at it with this type of eye? Well, the dots would be distributed within our grid, like so. Now, in our simplifying example, we are only assuming that we can see lightness or darkness. So what is the only thing we actually perceive here? Well, we perceive that there is a slight dark color in some of the grid spaces, and then there is the full brightness white color in the other grid spaces. Now, the question is, if I am a computer and I receive this imaging data from my sensor array, how can I represent this internally within my device? And the answer is actually with a NumPy array. Do you see how this could be a NumPy array? So we can represent images directly as if they are two-dimensional arrays. So I can take this array and represent it as follows. Does that make sense? This is closest way I can perceive the world. Now, okay, so you don't get bored, right? You can imagine that you have a bigger than 3 by 3 array, right? Okay, and separately you can imagine you have more than light or dark, right? So you can imagine this also representing the image of the quad, or the image of the classroom, or the image you are looking at on the screen, right? The only difference is we have more rows and columns. Now, if we want to store color data, we're also going to have rows, columns, and then we're going to have a little array in there that is the red, green, and blue values. We don't need to worry about that. Okay, so the task now is that I have this thing, and I need to somehow turn this into a 6. And if I get something else, and I'm not going to do all of the notation again, but for example, if I have 1, 0, 1, 1, 0, 1, somehow that has to turn into 4. You're going to hate this. I'm going to do this with vectorization. Yeah, that's right. I taught you vectorization because that's how machine learning works. What we need to do is we need to invent another matrix that we can multiply this matrix, this two-dimensional array, by in order to get 1, 2, 3, 4, 5, 6. The way this is usually done is not that we actually get that number out, but we actually have a vector. I know, I'm sorry. You didn't want to learn vectors, and then you asked to learn AI, right? So you have completely played yourself on this, okay? I was going to teach you something else. I don't remember what it was. Oh, I was still going to teach you the same thing, just from a different direction. So the only things we can perceive in our universe is whether we have the presence or absence of a 1, 2, 3, 4, 5, or 6. So rather than this spitting out 6, what we're actually going to get here, we're going to represent this 6 in a different way. I'm going to represent it as 0. Okay, I'm going to write 5 zeros. It's just going to take a while. And this 4 is just a 1 in the address 4 of a vector. So, how am I going to do this? Well, I'm going to start by saying, okay, I have some matrix which I'm going to denote as M. I'm going to multiply this matrix by something. And then I'm going to get as an output the vector, a vector of length 6. Okay. Does that make sense? I'm not sure you all like AI as much as you said you were going to. It's too much vectorization, isn't it?
Wouldn't it be 5 zeros in the next?
Yeah, so it's just a vector of length 6.
Oh, okay.
Of length 6. So we need to find what this matrix is, right? And we can find that with vectorization. Okay. I'm going to erase this portion of the screen, and then we're going to start building towards that, okay? There was an eraser somewhere.
Oh, there's one right here.
I very much feel like I'm gradually going insane trying to exist in three-dimensional space. Okay. When I first started teaching here, I only did board talks, and then all of my course evals said, we can't read your handwriting.
Don't worry, your Professor Battle's handwriting is so bad. Sometimes I can't read it.
Yeah, I kind of feel like
Yeah, true.
everyone could just be chill.
But it's, you know what bad handwriting means that,
You're a psycho.
you know, it
Don't
means
tell
that-
Professor Battle I said that. Okay.
means that you're, you know your stuff. Just like how doctors have really messy handwriting.
Oh yeah, and like the pharmaceutical shorthand for like different medicines, it's just like, it just looks like scribbles.
Okay. So, I have some array, which we'll just, I'm going to put in 3. This is going to be multiplied by some kind of thing. And it's going to give me, that's 1, 2, 3, 4, 5, 6. Okay. How do I decide what's in here? Well, first I'm going to decide what shape it is. And I'm going to decide what shape it is using matrix multiplication. Now, do I look like I know how matrix multiplication works?
I forgot I learned it.
Yeah, so what I'm actually going to do is I'm going to walk over to that screen. I'm going to change from capturing video to displaying my screen, and I'm going to Google matrix multiplication, okay? This is how machine learning was invented. So, what do? Turn off the video. Boom. Wait, turn it off. Okay.
Is that a face reveal, by the way?
My face has appeared in other content. Wait, why did I type in machine learning? That's what I'm trying to do. Matrix multiplication. Okay. So, here is the exact graphic that we want. Okay. Okay. And so, what are we going to do with that graphic? Okay. So, if we take an m by n two-dimensional array and multiply it by an n by p two-dimensional array, we get an m by p two-dimensional array. So, this thing is A with m equals 3 and n equals 3. We don't know what this is. And this is C, and we want C to be, I don't know if I want M or P to be 1, but one of M and P needs to be 1, and one of M and P need to be 6, okay? So we're going to say, well, that's actually easy. We can do P equals 6, and then we can do M. Really, we want M to be 1, but that means we're going to need multiple matrices in here. Okay. So, how are we going to do that? Well, we need our last value to be 6, which means we need to be multiplying by something that has a top length of 6 at some point. So there's going to be an intermediate matrix here that is going to be, I think, 6 tall. So there's going to be something that is of size 6. It's going to be multiplied by something of size 3? Did I make that up?
I thought it was 1 by 6. Like,
This is trying to be 1 by 6. But somehow I need to get down to 1 somewhere else, right? Oh no, okay. Yeah, I think I want this to be 1. Is that right? We can just get a 6 on one side first, right? So, if we want to get a 6 at all, we can just do a 3 by 6, right? So for example, we'll do 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. And if we multiply those together, that is n equals 3, p equals 6. Okay. And then we'll put something else here. Okay. And that will be I don't know. Math is hard, right? What do we need? We need to either get a 6 or a 1 back, right? Oh, we can get down to 1, right? Because if we do 3 by 1, we can conflate things. So, we're going to put a series of matrices here, and I believe the next one is going to be this size. We're going to multiply them together, and we're going to get a vector out. The problem is, we don't know exactly what numbers should go in each position in this grid. So what are we going to do? We're not going to, well, actually you could just put random zeros and ones there, which is what I did. We're going to put a bunch of random data inside this array. And this is where the learning step comes in. So we have these sort of intermediate filters. So these are usually called a layer. Here's a layer. And we're just going to put random stuff in there, okay? And the random values we're going to put in there, we're going to multiply them through, and we're going to figure out what we have over here. And in this case, for example, we put in 3. And maybe what we'll get back is, what do I think we're going to get back? I think we're going to get back, we're going to say that that is a 1 and a 2 and a 3. And what is the problem with this? Well, the problem with this is that this value is wrong and this value is wrong. So, how do we solve that problem? Well, you figure out, because each one of these matrix multiplication steps is going to result in some value coming up over here. And how is that going to work? Well, if we say this is B, then we say this is C, we can describe matrix multiplication, and let's go back on this page, by looking at each individual point. Or wait, where is it here? Looking at this equation. Can you see that okay? That's way too small. There's no way you can see that. I don't believe you. Okay. So we're looking at this thing. So Cij will equal the summation of, do you know what a summation is?
Yes.
I'm taking the sum over a vector, right, basically. In scientific computing. In mathematical notation, it's different. So I'm going to take the summation from 0 to n. I'm going to say I equals 0 to n. Why is that? Because I'm going to do it for each one of the things that lines up. And I'm going to take, I think it's a1i, right? Yes, a1i. Shoot, I can't see it. ai1 bi1j.
Or just B1J.
Yeah. It's I1 times, so this, I'm doing x for multiplication, or like however you want to do it. It's really hard for me to write multiplication on the board. Maybe I'll do an asterisk. Okay. And then that's going to be b, oh shoot. Yeah, right, it's j. Okay. I, j, j, I don't know. We're going to sum each of these things up. To me, that looks terrible and confusing, so I'm actually going to implement matrix multiplication in Python now, so we all know what we're talking about. Turn this off. Okay. This thing didn't have a cap on it, right? Okay. So, how long? Oh my gosh, I only have 20 minutes. This is so hard to teach, by the way. Okay. 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 Matrix mult. We'll do setup. Setup. Our input is a 3 by 3 grid of zeros or ones. And we're going to have an example. The array 3, oh, I need NumPy. Import NumPy as NP. So I'm going to type in what 3 is, which I have on the board. mp.array of 1, 0, 0. Is this right? 0, 1, 0. I need commas at the end of these. Zeros, 0, 1. Okay. Okay. And this represents the 3 side of a die. Okay. So how are we going to matrix multiply? Oh no, we want to say what output we want. Target output. we would like to teach a computer program to determine this is a 3, perhaps by outputting the following, which would classify. I haven't introduced the term classify yet. This is a classification problem. I am taking types of images and I am trying to sort them into classes, such as the class of die that represent 1, die that represent 2, die that represent 3. Which would classify. So we're going to call this 3in. Oh no. I don't know if this formatting is going to work. Okay. And then we're going to have 3 out. That is going to equal np.array 0, 0, 1, 0, 0, 0. Okay. We need to find some matrix by which we may multiply. That's not even true. We need to find some function by which 3n can be transformed into 3 out. We want to learn this function, so we will start with a random matrix, then refine it. Okay. So, let's render this. I'm typing as hard. Quarto render ai.kmd. Let's see if this looks reasonable at all. Okay. Open ai.kmd. What? Oh no, I opened the QMD. That's not what I meant to do. Stop, go back. Okay. Open ai.html. Does that sound right? There it is. Okay. So, this is what I'm working on. Okay. And the way we're going to do this gosh. There we go. We use matrix multiplication. So, with matrix multiplication, I'm going to write LaTeX, and I'm going to check the reference multiplier. Okay. Wait, I can just borrow this. Okay. So, does this look confusing? No, it's trying to trick you into thinking it looks confusing, right? This is totally fine. I'm able to check, I think, probably all of this and see if I can render it successfully here. Copy. Copy. I'm putting it inside of double dollar signs because LaTeX is cash money. That's how you remember. So, I'm introducing my matrices. And that is going to equal so let's see. Given, oh wow, this is hard. Okay. Given two matrices, A and B. I'm going to make a note. You're going to be confused looking at this. You already look like you've completely checked out. That's okay. What you're learning now is linear algebra, which we capitalize to denote they are matrices and not values. This is going to be slightly easier to look at because I'm going to use capital letters to represent a matrix. We can calculate the product C as follows. Where's C in here somewhere? And how does that work? Blah, 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 all of this stuff. Okay. I think that's fine. I might have to rewrite that. Okay. So, in Python, let's write the function in Python. What is this? This is looping over I and j values given to arrays. So we're going to have a function that I'm going to call mmult. It is going to take A, which is a matrix, and B, which is a matrix. It is going to return some matrix C. So we're going to create C, and what is C going to be? We're going to make an array that is the same size as the, well, it's m by n. Okay, let's make a note. A is m by n. B is n by p. C is m by p. Okay. So how are we going to do this? M is the length of A, and then P is the length of B0, because, why is this? We want to take the horizontal size of one of them and the vertical size of one of the other ones. So we're going to look at the first entry and then take that size. We're going to make C that is this big, but we have to do one other thing first. If len of A0 is not equal to len of B, not equal to len of B, what does this mean? This means we can't multiply the two matrices because the inside sides don't line up. So we can't line up all of the vectors properly. So this is going to explode. So C needs to be an empty array of a certain size. And so how big is that going to be? I'm going to put, I guess, nones in there for now. None for I in range P, for M, or for J in range M. And for now, we'll just return C. Okay, so let's look at an example. We will first make some A. And I'm going to make a relatively easy A. I'm going to do 1, 2, 3 by 4, 5, 6. B has to have the same interior length, so it's going to be of size 2, and we're going to do 7, 8. We'll only do 7, 8. I think that's fine. That should be fine. And then we are going to look at mmult of A and B. I think that's going to work. Okay. Oh, where's my error? Let's see. I think I have the wrong types of parentheses here, so I'm going to close my list. Int has no length. This has to be a two-dimensional array. These could be NP arrays. I'm not putting them in NP arrays for now. Okay. So what do we have here? Is that too small? Okay. I take a 2 by 3 array, and I multiply it by a 1 by 2 array, and I get, I think, a 2 by 2 back. So m is 2, n is 1, t is 1. Wait, no. I don't know. Some numbers or something. Okay. Okay. You get an m by p back, which is the length of A is 2, and the length of B0 is B0 is also length. So that. Okay. So now, what can we do instead? We don't have to put none here. What we can do instead is we can expand this out into being a for loop. So for I in range n, I'm actually just going to print problem bad return. Okay. For I in range, the outer one is m. Okay.
You're missing quotes on that.
Thank you. So what are we going to loop over? We're going to loop over n. Okay. For n, what do we want to do? We want to say we're going to add up a sum. Sum will start with 0. So we don't want to call it sum. Val. Okay. Oh, we do want to do this for all of them, because we want to do this for every point. Okay, so we're going to have many loops here. For I in range m, for j in range p, what is this? This is going to be each point in the output. So this is I1, J1, IM, JP. So that's why we have the same loops. We're using I and j to refer to the values ranging from m to p. Okay? How are we going to calculate those? We're going to sum them. I'm in visual mode. And what sum are we going to calculate? We are going to take A, I, okay, A, I, let's see, A, I, oh, this can't be I. This has to be I, J, K. AIK times, making this big, BKI, right? No, it's BKJ. And we add that to sum. Okay? And that, or no, we add that to val. Okay, just pausing right here. Do you see how this is a vector operation? We can rewrite that as a vector operation. We'll get it to work, and then we'll turn it into a vector operation. But this is multiplying k values times each other and adding them up. This is a sum of a vector op. C, I, j equals val. Kernel died. Ooh, that's sad. I've never seen that before. Okay. Let's see if the error is here. I might not be able to debug this in 4 minutes, depending on how bad it is. Okay. Why did the kernel die?
What's the kernel?
So the kernel said so somewhere. Sometimes it says like starting Python kernel. Yeah, there we go. So there's this program that runs in the back that they call the kernel, and it's just Python that's running, but we don't see it. So the computer has its own version of Python, and Quarto is going to ask that version of Python to solve problems. But for some reason, the kernel like vanished or something. I don't know why that is. Yeah, the kernel died. Okay, I was feeling morbid thinking of it as having died, but it's telling me it died. I will fix my kernel someday. It is not surprising that training a computer to understand what dice are would cause the kernel to explode, especially while I'm live coding it. Think carefully about your choices of asking me to explain AI to you, discuss amongst yourselves, and I will either teach you AI for the remaining 5 lectures, or we can do something else. I would rather do this, but it is up to you. Have a nice day. Yeah, class is over, right?
Yeah.
Okay.